Briggs, time for another episode, 67 of Uncertainty and Probability Theory, the Logic of Science. Well, we have finally reached models. This is the point at which I think everybody wanted me to start. And it's a good idea to start at models because this is the way most classes, if you take a statistics class or a class on evidence or even an AI modeling or something like this, they start with these models. They just go ahead, write it, and start with the models and then try to get you to understand the operation of these models, the guts, the mathematical innards and things like this. And all that's valuable, has worth, all this, no question. But you will make all the same mistakes and you'll become so ingrained in those mistakes that you'll think there's no other way but those mistakes. So I wanted to take, I don't even know how long we've been doing this now, well, it's been well over a year, to really imbue in us a proper sense of uncertainty and certainty. We built from nothing, absolute nothing, literal nothing. And we built from that, from our understanding of nothing, from our understanding that we could understand, to a system of probability, which we understand as the completion of logic. Logic and probability are the same thing. And we built all of that up from absolute scratch. And we arrived at this point. Now we can apply this in a systematic way, and the way that most scientists and everything apply it. But I want to, we discussed all manners and ways of handling evidence and thinking about evidence and causal questions. And our goal has always been to understand cause. And that's what we want with models too. If we have the full cause of a certain thing of interest, the formal, the material, the efficient, and the final cause of that thing, whatever it is, and the conditions under which that cause can be brought about, because not all substances, even if they have certain powers, can bring those powers into operation and cause things to happen unless conditions are right. So we need to understand both the cause and the conditions. And if we have a model that does that, which is incredibly rare, but we can have them, then in science anyway, but then we're fine. But almost all the time we're working with correlation. We don't have the cause. We might have some causal components in the model, but we don't have the full cause, and we don't have the full conditions under which the causes are operative under what other substances or substance that we're dealing with. So we're going to be stuck with correlation. And now we're going to do the philosophy of these models, and I'm going to use regression, something called regression. And I'm not going to talk about I'm going to use this model called regression, and only because everybody else does it. And it's the most popular model in use. It's the most ubiquitous. It's found in, it's just everywhere in medicine and psychology and all the so-called soft sciences, all in economics, sociology, education, on and on and on and on. Absolutely, climate change, everywhere regression is used. And I'm not going to talk about the mechanics of it today. I'm going to provide code on the blog and on Substack, wmbriggs.substack.com. And you could follow along with the particular example I'm going to give today. But I'm not going to go into any of the math or the guts of it this way. In doing it the right way, I only want to concentrate on the philosophy of this model. And I don't really care about the mechanics of it. They're not of interest to us today. Next week and for future weeks, we'll do mathematics of models and so forth if we're really interested in building these kinds of things. Which there's any number of sites that can teach you how to do that. And you don't need me for that. You need me to teach you to understand what these models mean. That's the most crucial thing. So we did an example. So I got, there's going to be a link. Grade point average. There's this site that's in R. I'm going to use the software called R, which you could look up. It's a free software. It's the most widely used statistical software. I don't care what software you use. I'm absolutely indifferent to that choice. We're not here to build software. We're here to understand. So if you want to use a different tool to use, that's, God bless you. Go ahead, use whatever tools you like. Not interesting. But there is a data set in there. They collected a couple of hundred observations on grade point averages at the end of their first year for a bunch of students, and among other things, they collected whether or not the students were white or non-white. And today we're only going to deal with this race marker. So we have a bunch of grade points, and we have a bunch of markers whether or not the person was white or not. Now, was the grade point measured accurately in this data set? I have no idea, neither do you. No idea what this is. We could read the description, we could take their word for it, which is what everybody has to do, and in the end, which I'm going to do and you're going to do with me, we're going to take their word that all this stuff is accurate and so forth. We don't know what the grade points of the classes. We just know, we don't know what subjects all these people took. We don't know any of this kind of stuff today. We just know here's a grade point. We know that from the rules of the grade point, they can go anywhere to 4 to 4.15. Grade inflation means not only do you have 4 points as the maximum, you got to push the maximum a little higher, but whatever. That's their rules. For whatever reason, their grade point goes from 0 to 4.15. What about race? Well, colleges and universities are, you know, absolutely ridiculously preposterous about race. So are all these markers correct? White and non-white? I have no idea, and neither do you. We're going to take them as written because that's what we have to do. We have to take these things as given. Now, non-white can include non-white can include Asians. It can include blacks, you know, Hispanics, if they mean something like that, or any number of things. So I don't even know what non-whites means, and neither do you, and because this is all we have. Now, I'm going to show you. I'm going to do my best. I'm going to put in a. I'm going to put in a picture. I'm going to put a picture of these grade points in. I'm going to try to put a picture of these grade points in, you know, over the top of this video, because our first duty is always to look at this data. I mean, that's mechanicals. We'll talk about mechanics and all that kind of stuff. You know, you've got to examine the data. Did somebody put in a 41.5? You know, are there typos in the data? And obvious things like this, which, you know, all that's important, very important, even extremely important and so forth, but we're just going to bypass all that and assume it's correct. And the reason is because this is a sort of a well-used data set and so forth. So I'm going to ignore all those niceties, which you cannot in real life ignore, but today we'll ignore that kind of stuff. So, but we have to look at it. And so one way of looking at it is this histogram. And in case I don't get it, there's going to be there's grade points. It goes 1, and here's 4.15. Out here, and here's 0, and there's 2, and there's 3, and there's 4, something like this. And the whites look like this, and the non-whites look something like this. This is whites, and this is non-whites. Now, I'm going to, if I don't, I'm going to try to insert the actual picture that I have here. So, which we could do. Now, I want to ask you what I think is an impossible question. It's impossible, if you've had any formal training in probability or statistics at all, to answer this question. But I'm going to ask it anyway for those people who haven't had training, and I think they're going to get the answer right, and whereas those without training, those with training will probably get it wrong or find it impossible to answer. Here's the question. Pay close attention. Are whites and non-whites different? Well, obviously. Otherwise, we wouldn't have been able to code white and non-white. Whatever they meant by whites and non-whites, this is what they coded as a difference, so they're different. Somehow or another, somebody identified these differences. So yes, they are different. Oh, that's not the question we really mean. Are they different in GPAs? Well, here's the picture we have of them. Are they different? The answer is yes, they are. That's our hypothesis test. We look at them. They all didn't score the same. They all don't have exactly overlapping histograms of this kind of, or this kind of thing. If they were all exactly the same, if we had 100 whites and 100 non-whites, and there were 10 who scored 1, and 10 who scored 1.1, and 10 who scored, and so on, and everybody was identical, then we'd say, yes, those people are exactly the same. As it is, they had differences, so they're different. We have just passed we have conducted a hypothesis test, and we didn't need to use math. All we needed to use is our eyes. They're different. They are absolutely different. They are not the same. We're done. And if all we wanted to say, was something about this group of kids here, I presume they're kids, I don't know, but these individuals anyway, if all we wanted to do is say something about them, we're done. We're finished. We don't need any math. We don't need any statistical tests. We don't need any distributions. We don't need anything. We have the results of our eyes. Here it is. They're different. Now, let me ask you this question, which I think is an easier question. What caused the differences we see? Well, the answer is, I don't know, and neither do you. Here's two possible causes. There's two possible causes. One is whites are sometimes, often, in this case, we might often intellectually superior. Intellectually, but they can't spell. Intellectually superior. And so therefore they have higher GPAs. That's one hypothesis. Here's another one. Whites used racism to depress scores of non-whites. Sometimes. Those are two hypotheses, that whites are intellectually superior sometimes, or that whites use their powers, their occult powers of racism to depress the scores of the non-whites. Both of those causal hypotheses, these are causal hypotheses, are equally well supported by the data that we have. So if you're going to apply some statistical test or do anything with this, any kind of model that you can manipulate, do things, whether it's AI or it's regression or whatever you're going to use, both of these are equally well supported by this particular set of data. So you can go away from this and come away and say, my hypothesis is perfectly supported by this data, and you could attach all kind of standard measures to them, which we'll do next week. But for right now, the right way is, of course, we can't tell. I have no idea. I could bring in outside information. Of course, I can always bring, I'm trying to keep ahead of my notes here, so I follow the notes carefully, because I want you to read the notes this time too, as well as look at the video, because there's going to be some differences. Now, I can bring in any kind of outside information that I like. It's absolutely fine. And I can make judgments based on that outside information. Perfectly fine. We do this all the time, but that's not this particular model that we're going to do, and then your task then becomes to justify that outside information, which has nothing to do with this and all to do with you justifying that particular knowledge, which may back up one of these two things. But if we're just going to use this data, we have this, and we must remember, how many other hypotheses equally fit this data? Well, that's right, equally fit this data? There's an infinite number of them. There's an infinite number of them. I tried to show you that time and time again. For any set of data, there's always an infinite number of models that explain that data perfectly, which is even a wider set of models that can explain that data imperfectly, like one of them is regression. So now, I already know all about these people. I need do nothing else if this was our only thing. I don't need to have a model to say whether or not there's a difference. I can see that there's a difference. There's no, probability does not exist for us. It's not out there drawing observations and GPAs and all this kind of stuff. So that's not what's causing GPAs. GPAs are caused. Every student has a GPA, which means he had a certain number of classes and he studied more or less for all of these classes, and the tests were more or less difficult, all this kind of stuff. And some days he had indigestion and some days he didn't. Some days he was hungover and some days he was not. All of this stuff goes into a GPA. What's the cause of an individual's final GPA of 3.85? We don't know. We're not going to get that answer from this kind of data. We cannot do it. So any model we have is correlational. If we have an interest in saying something about new data, we can use this particular data as long as we think the new people will be like these old people in the causes and conditions that brought about these GPAs. What are those causes and conditions? We don't know. We don't know. We don't know. We already got done saying we don't know. All we have is this particular place, and they have this particular data, and we say, well, if we're trying to talk about data we have not yet observed, it doesn't have to be new. It could have been taken in the past as well. So whenever I say new, I don't necessarily mean in the future, okay? If I mean in the future, I'll say so. But for us, new always means not yet observed or not yet accounted for in whatever models that we have. Even if we have observed it, but we haven't used it in the models, it's still new. If we want to say something about this new data, which we haven't yet measured, we're uncertain. And if we're uncertain, we could use probability models to say something about it. And we'll use regression, because everybody uses regression, so why not use regression? Now we have some problems here. We need to think about it. GPA. Suppose everybody had one class, only one class. This was whatever this was, some sort of academy or something like this. Everybody had one class. Therefore, everybody will have, and the grade points would be 0, 0.5, 1, 1.5. These are the possible grade points. I'm just guessing. These are the possible grade points everybody could have. 4, and then somebody gets a gold star at the end for being teacher's pet. They get 4.15. These are the grade points that we could have for every given student. Now this is a discrete, finite set. There's a lot of information in this video. I'm trying to pack it all into 30 minutes. This is a discrete, finite set. There's 1, 2, 3, however many are here. There's 8 or 10 of these, whatever there are. That's it. There could be no other GPAs except for what's in this set. I hope you agree about that. It's discrete. It's finite. That's it. That's all we can have. The same is true if the kids had more than one class. If they each had 2 or 3 classes, or they had any number of, we don't know how many classes each kid has. We're not saying each kid had the same number of classes. We have no idea. But even if this set is expanded to 0, 0.01, 0.02, and so forth, all the way up to 4.15. This is still a discrete, finite set that GPAs can fall into. This set, these number of buckets, and none other. That's it. All of our real-life measurements are like this, discrete and finite. Not just GPAs, but all of them. Therefore, we would do best if we had a model which assigned uncertainties to these discrete, finite number of buckets and no others. After all, we don't want to have assigned probabilities to -1 GPAs, do we? Because they're not possible. Or a GPA of +5 or some absurdity like this, because it's not possible. So why not have a model that does that? Well, that's work. We can construct such a model. We could have something called like a multinomial. We've discussed those before. We could have such a model. Absolutely fine. But that's real work. And if we're doing that kind of work, it takes away from time we could spend writing grants and things like this. So we're not going to do that. We're going to use a normal model instead. And you know what a normal model is. I'm not going to show you the math of it, but you know, it's the familiar bell-shaped curve thing. And a normal model, we'll just say, now we have a choice. A normal model is specified by 2 parameters. One that specifies the central part of it, where the center of it is, and another that specifies the spread. 2 parameters. Once we specify those 2 parameters, whatever they happen to be, we have our normal distribution. We can say our uncertainty in future GPAs is quantified by a normal distribution. That's regression, okay? That's all regression is, using a normal distribution to quantify our uncertainty in whatever it is we're interested in here, GPA. Now we know this is strictly wrong, because a normal distribution lives on the continuum, which is the uncountably infinite numbers from -infinity to infinity. So it's strictly wrong. It's just going to be an approximation. As long as we keep that in mind, we'll be absolutely fine. If we don't keep it in mind and we become addled by pagan mathematics and say nature is drawing from normal distributions and some weird occult rituals that people have about these kinds of things, we're going to make ourselves crazy, because that's not the way it works. The real thing is, all these GPAs have myriad causes for each individual person and so forth, and our uncertainty in them is not the same as the causes themselves. We're not going to make the deadly sin of reification. We're not going to do that. Anyway, so now we have a choice. Well, we have this white race marker here, white, non-white. We could have whites have their own central and spread parameter, both for their normal distribution. Non-whites can have their own central and spread parameter. So in other words, we could have, here's, for instance, non-whites. I'm just exaggerating this wildly here. So we can have the difference, and here it could be whites. This one has a sharper peak, meaning it spreads less, and the central part, of course, is different than the central part of whites, smaller. We could do that. But what most people do when they do regression, because that's work, we could certainly do it. Just like we could certainly do the real model, but we're doing normal distributions. What normally what happens is the spread parameters are both will be the same, and the central parameters will be different. Yeah, it's a way to do things. In other words, we'll just assume the spread parameter is exactly the same for both whites and non-whites here in our model, and we'll let them have different central parameters. Now, we've specified the model, a normal model. We know it's wrong, but it's going to be close enough, we hope. We'll see whether or not it is. And we have these parameters. Now, do we know what the value of these parameters are? No, we do not. Nobody in the world knows what these parameters are because one intelligent reason. They do not exist. These parameters do not exist. Normal distributions don't exist. Neither do these parameters exist. We've already ascertained and deduced, we have deduced from the rules of this GPA game that GPAs can only live on these particular things. And if we're going to be talking about a number of new people, that number will be n, and will always be less than infinity. However many people we're going to be talking about in the future that have GPAs, it's not going to be infinity. Infinity is an unimaginably large number. So our n will be finite. We don't need to worry about any of this kind of stuff. So we're only going to be talking about some finite number of kids, and we want to quantify our uncertainty in GPA. We know we need to specify these parameters to have our approximate model. We know these parameters don't exist. They do not exist. There's no point, therefore, arguing about true values of these parameters. There are no true values of these parameters because they don't exist. Because the normal model doesn't exist, because GPAs are only finite and discrete no matter what n is, as long as n is finite, which is absolutely no restriction because n always will be finite. I'm going very fast. I've already gone 22 minutes. I got 8 minutes left to pack all this into one lecture. So this is very information dense. You're going to have to listen to this twice or read the description. And I haven't even got to that. I know I'm going to go over time again. And I apologize for that. I'm always going over time. Okay. Now, because we specify these parameters, we don't know what they are, and we want to use a normal. We have to specify our uncertainty in them because we don't know. One is 3.5, and the other one is 3. We don't know that, the central parameters. So we have to specify our uncertainty in them. There's any number of ways to do that. What's the correct way? The correct way? None. None of them are the correct way. You'll hear a lot of bickering about this. Bayesians call their specification of the uncertainty prior distributions. Prior distributions in these parameters. Okay, that's a fine name, whatever. I don't care. And then they bicker about what's the best way. Should we use maximum entropy? Should we use conjugate priors? Should we use flat priors? Meaning we'll let the possibility that these central parameters can be any number from negative infinity to infinity with equal probability. Well, that's a complete fiction. That's a lie. But the math works out nice if you do that, so we'll handle it that way. As long as we keep in mind it's an approximation, maybe that's not bad. For our purposes today, we don't care. We're going to use what the software gives us, which is something called a conjugate prior. We don't care. We don't care. Our interest is not in these parameters. We don't care. We're not interested in these parameters in the least. If we pick a different way of specifying uncertainty in the parameters, we will get different resultant probabilities. That's not a bug, it's a feature. If we pick a different model, we're going to get different probabilities. If we use a gamma distribution instead of a normal distribution, we'll get different probabilities. If we use this multinomial proper distribution here, we're going to get different probabilities. If we use a Weibull distribution, we'll get different probabilities. Every single model that we pick will give us different probabilities. Which of them is correct? None of them is correct except this one here, the one where the deduced model is always correct. Which we don't do. We're not going to use the deduced model here. We're going to instead use this approximation because everybody else does. That's our excuse. And we're using this parameterization scheme because everybody else does too. And then we're going to set our prior uncertainty on these things in the way the software does as a default, because everybody else does that too. And there's absolutely nothing wrong with it. These prior specifications, there's well-known mathematical results about this. They have some effect, but as long as the data set's marginally big or something, they mean very little. They change the results. They do change the results, but very, very tiny. And as the data grows and so forth, they become almost negligible. So we're not going to spend time fighting about them. Okay, so that's what it is. So that we do this, we put this old data into the software and the mathematics, and we just say, well, I want to know the probability. I have to erase something now. I'm sorry. I want to know something like this. I want to know what's the probability the GPA will equal G given the old data, the model, and its parameterization scheme, and all those assumptions and everything that we went into. Assumptions. Okay? Oh, and also, I want to do this for race. I want to do it for whites and non-whites. So I want one probability, the probability the grade point will equal some G, whatever G happens to be, if I'm interested in G. G equals 2, whatever. And I condition on the data, the model, the assumptions that go into all that kind of stuff, and whether or not the person is white. And I can calculate both this for white and non-white. And the probability will equal, this probability will equal 0. It doesn't matter what G is for any G, for all G, because, oops, the normal model lives on the continuum. And what's the probability of pulling out a number from an uncountably infinite number of numbers? 0. So no matter what number we pick for G, our model fails us. So we have to do something to fix that situation, because the normal model just won't tell us. Just won't tell us any G. It says the probability of 0 is seeing any grade point, and it's true, conditional on the normal model, the probability is 0. So one thing we could do, and here comes picture number 2, is we could put that normal model back into our buckets. We can give the probability of those buckets that we have deduced. We know what the buckets are going to be for the number of students, that kind of thing, or approximately there. And we could then give probabilities for individual grade points. All right, so you'll see if I did it right, it'll be one distribution like this. And if I draw them right, this will be white and non-white. And here's the GPAs down here. These are the GPAs, the new GPAs that we'll see. And that's as a result of making discrete those probabilities. If the normal distribution does not give us discrete probabilities because everything is 0, so we'll make little buckets. We'll make little buckets of about, I think I did, boy, I can't remember now, like 1/20th of a point, like 0.05, something like that. I don't remember. It's either 0.05 or 0.01 grade points. Whatever, you'll see the picture. And you can change it to make it whatever yourself. Which is the proper one, by the way? Which is the proper discretization of this normal distribution? There isn't one. There absolutely is not one. There is absolutely no. I'm afraid I'm going to have to go past 30 minutes again. I'm sorry about that. I should have tried to bite this off into two lectures, but I did not, and now I'm stuck with it, and so are you, and I apologize for that. I have never been able to stick to 30 minutes. I'm up to 28 and a half, or almost 29 minutes right now, and there's absolutely no way I can squeeze it all in. So we want the reason we did this discretization, now I can slow down a little bit, seeing I'm not going to make 30 minutes. We wanted to squeeze everything into this normal distribution. It's not possible. It gives us absurd answers, like the probability of seeing any observation is 0, which is absurd. So we can make little buckets. We can make little grade point buckets, from 0 to 0.05, from 0.05 to 0.1, to 0.1 to 0.15, and so forth. Or 0.0 to 0.01, from 0.01 to 0.02, whichever the left and right are, you decide, left inclusive or right inclusive, that's up to you. The discretization that you pick is entirely up to you. There's absolutely, positively no right answer. There's no right answer. There's no probability that says you have to do this discretization or that discretization. It just doesn't happen, all right? Because it depends on the questions you're going to put to this data. What are you going to do with this model anyway? Why are you calculating this model? Why are you interested in the uncertainty of future GPAs? We already know we can't say anything about the cause because there's no causal measures in here except the possibility of race. But we don't even know what's going on with the race per se. There could be Asians in there who usually score better than whites. There's blacks in there who usually score worse. So it's a whole mix. It just says non-white. So what's going on with the cause? We don't know. So because we can make this particular pronouncement over here saying here's what I think the GPAs will be like for whites and here's what I think the GPAs will be like for non-whites. And the way I drew this, as you'll see when I dropped it in, I hope, is they're symmetric. They have exactly the same width because we specified they would have the same spread parameters, which I erased, just different central parameters. So we specified that. That's why they look identical. And there's some jaggedness to this too, by the way. They're not quite perfectly sharp. And that has to do with the numerical approximation. This particular probability, the calculation involves numerical integration, which we come at approximately. We have the normal distribution itself is an approximation, and the integration that we're doing is also an approximation carried out in a numerical way, which in no way blesses the results because we turn a blind eye to the randomness. We already covered the so-called simulation and the gremlins inside MC models and all this kind of stuff where people think, well, I know my numerical integration is right because I'm drawing from these normal distributions and calculating. All that's nonsense. It's great nonsense. It's just a useful method of doing, it's not even that useful sometimes, but it is a method of getting a integration where you can't get an analytic. Well, in our case, we could with our conjugate priors and so forth. If that's even what the software is using, I can't remember. We can get analytic results, but in this case, we don't because nobody else does. So there's some discretization in here, but it doesn't matter because this is the integration method. The integration is one of the assumptions that we put in here. Given the particular integration that we used, here's the probability that we're going to get in the buckets that we formed after the fact, okay? That's absolutely all that means. This is just one more of the assumptions. If we change any of these, if we add or subtract a data point or many data points, we get different probabilities, as we should. If we change the model, we get different probabilities, as we should. If we change the model, then we change the assumptions. Or we keep the same model, but we change the assumptions on the parameters, we get different probabilities, as we should. If we change the model, which changes the parameters and the assumptions, we get different probabilities, as we should. If we change the integration, all the data points we put into the integration is just a bunch of little data points. If we change any of those, we add to one or subtract one, we get different probabilities, as we should. All right? This is not a bug. There is no right answer in probability, except for the fact that once we specify all our assumptions and the question of interest, we deduce this probability. All probability is objective in that way. This is the subjective part of probability. This is the subjective part of probability. We covered all that kind of stuff before. So it's in no way a weakness that we change the integration method, we get different probabilities. That's just the way it is. Now this whole thing is, again, just an approximation. Now I can calculate. I don't have to calculate. Now I can calculate exact probabilities. If I want to know the probability of, now if I want the probability of G being equaling to 2 for whites and non-whites, I can't get 2, but I can get the bucket that's, you know, I don't know what it is. I can't remember what the discretization is here, but suppose it is 2 to 2.05. And I'll call that'll be my G. That'll be the bucket G right there. If I say, what's the GPA between 2 and 2.05, I can get an answer. I can get a probability. for whites and non-whites. Or I can ask this, what's the probability that the GPA for whites will be greater than the GPA for non-whites? Any random, some brand new white guy and some brand new non-white guy given the same, all that same stuff over here. I can calculate that, and I did for my particular stuff, and it came to be 6.69. Is that the question everybody should be asking? No. It's a question I thought maybe it was a little interesting. Maybe it's not interesting to you. What's the best probability question we can ask here to say something about these differences? There isn't one. There is no best probability question to ask about this that's going to give you a formula, a one-size-fits-all formula and decision that fits everybody in every situation. It does not exist. So, is this the right question to ask? No. Is this the right question to ask? Maybe. For me it is, because I thought it was interesting. And for you, maybe it isn't interesting. But this one's kind of fun in a way, but suppose the answer was 0.5. Suppose. Suppose that we guessed the GPA the next white person coming down the pike and the next non-white person coming down the pike. What's the probability of a white person to have a bigger GPA given all data, the model, the assumptions, the integration method we used is 0.5. That's the same as saying I don't know anything about two people except that they'll have a GPA, right? That says that race is not informative for this particular question. For this particular question, race is not informative, and only for this particular question. That means knowing the race doesn't tell you about any differences in the GPA, but it in no way indicates there's no causes going on between the races. You haven't disproved the lack of a cause. This is crucial. You have not disproved cause. You just said that race doesn't tell you anything about, because there could be, in all this old data we have here, sometimes the whites were doing intellectually superior than the non-whites, and sometimes they were using racism to depress the scores of the non-whites. Both of those could be true in the same data set that we had, and therefore the probabilities came out so that knowing a person is white or non-white, we don't know what was going to be the case. Or any number of different possible causes could exist in here. So we have not disproven that there's no causal actions going on. We have just proven that we don't know what they are. And all we've proven was that race is not telling us anything. We have not disproven a cause. We haven't proven a cause. We haven't disproven a cause. We've said nothing about cause. We bring cause to models. That's not going to be the first time I'm going to say that. We bring cause to these models. All right? We don't extract cause from these models because all models only say what they're told to say. Now, you've heard me say that before. All right, I think that's probably it. I mean, we haven't done everything. We haven't done possibly, we're not even close to being everything. How do I know this is a good model? Is this a good model? This normal model? Maybe it is for me. Maybe it stinks for you. Oh, we have done one more thing. Yes, I'm sorry. There is one more thing I wanted to do. Yes. I'm glad my memory told me about this. I can calculate, it's kind of fun. I can calculate the probability that GPA is greater than 4.15, given the same conditions, white, non-white, that kind of thing like this. For non-whites, it turns out to be, I think it's 0.01. I can't remember the exact numbers. And for whites, it's 0.15 or something like this. I don't remember. Now, this is called probability leakage. Probability leakage. We know from the rules of the GPA, one of our assumptions, that it cannot be greater than 4.15. So based on that knowledge, what's the probability grade point will be larger than 4.15? 0. Right? It's impossible. We cannot get a grade point larger than 4.15. With this model, however, I don't remember what it is. Maybe it's a little bit higher. Maybe 2% chance or something for whites of someone scoring a grade point of higher than 4.15. That's because our normal model, here's 0, here's 4.15, our normal model leaks here's an exaggeration. Our normal model leaks. These should be the hard boundaries, but we have some probability out here and we have some probability stuck out here. Is this 1%, 2%, whatever it is? I have the exact numbers in the code there on the website, wmbriggs.substack.com. Is that big? I have no idea. I have no idea. There's no right answer. There's absolutely no right answer. It depends on what you're going to do with that model. But from this, we can deduce several things. First of all, the model is leaking probability. It's giving probabilities to impossible results. Whether you consider this a harm or not, again, is depending on what you're going to do with that model in the first place. Why are you even calculating GPAs for new people? Again, you can't say anything about cause. Maybe you just want to know because you're handing out gold stars and you want to know how many gold stars you got to buy if you're the bursar at the university or something like this. Or you got to hand out of course, nobody is ever shamed for a poor grade anymore, so they're not going to buy little frowny face stickers or something like this. You know, a little frowny face if you get below a 1 or something. Nobody would get that. That's hurtful. We don't want to create an unsafe environment. So that's not going to happen. So what it does prove, though, it's more proof, we already had the proof, that the parameters don't exist. The parameters for our new model are irrelevant because we don't really care about those parameters anyway, because we could ask any probability question we want. We could ask, what's the probability a white will outscore a non-white by 2 on the grade point scale, or 1, or will be twice as high, or only half. We could ask any question we like with this. Like we can all the probability that I've taught you from day 1 a year and a half ago. We could ask any question we like in probability, and we have the model, our assumptions, and we can calculate the probability of that. This approach in modeling is the only way to go because it's answering the questions we want answered. But because of things like this, now this probability leakage, I should say, in this particular example, and we'll see next week in the wrong way, can be much bigger than this. It could be 10, 20%, 30%. Probability, probability only exists on 0 to 1, so we're giving away a lot, but it's never noticed because of the wrong way. People never notice there's probability. They don't care. Their focus is on the parameters alone or on hypothesis tests or something like this, which are absolutely meaningless and wrong, always a fallacy, which we've proved so many times we're sick of, but next time we're going to do it again to get even more sick of them. That's it. Are there ways to test for how useful this model is? Yes, there are. Yes, there are. And the best test will always be you use the model, make decisions with it, whatever decisions are relevant to you, which may not be in the least bit relevant to me. And are those decisions good for you or bad? And that's up to you to decide. There are some mathematical ways that we could say, well, if your decisions look like this, mathematical shape, maybe they do, maybe they don't, then the model may be good or may be bad. We can say things like that, and we'll do those kinds of things. But every model, it doesn't matter if we're using AI in place of regression, every conclusion is exactly the same as I made here today. It doesn't matter if I'm using normal or some other distribution or whatever. Whatever fancy model that you think you've come up with, everything is exactly the same. The philosophy is not changed by whatever changes you make to that model. So that's it. That's all of modeling. And every single model will be exactly like this. There's all kind of niceties. What if we don't have a thing that lives on some discrete finite number of buckets like GPA, and it's just yes or no, on or off? Or what if it's somebody who is going to die or live, or only going to live so many days? There are all kind of ways we can mathematically formulate these things, and we'll get to all those. There's some fun to be had in that kind of math and everything. But the math is always beside the point. The math is just the mechanics that get us there. The philosophy is what drives us to that math in the first place. We must not forget that. We must remember that the math is just a tool. The philosophy of how we use it, that's the most important thing. Always, absolutely always. And next week when I do it the wrong way, we'll go over that again. We'll do it the wrong way, the way everybody else does this kind of stuff, to show you the mistakes that can be made and are made. absolutely all the time. And your homework will be to go out and find any paper, go to any scholar.google.com, find almost any paper, any sociology paper, psychology, climate change paper, medical paper that uses this regression, and you'll see what I'm talking about. All right, wmbriggs.com, wmbriggs.substack.com, and I apologize again, I went way too long, but I wanted to fit it all in one episode. That's it for now. Thank you.